So V1 dot gradient vector f is equal to 0. This should give the equation of the tangent plane. Right, sir?
Okay, so see the gradient itself is a tangent, right?
Gradient is tangent.
See, the thing is, what you're doing there, the dou by dou x, that is a tangent, that is that is a slope one, right? That gives you the slope, right?
The gradient is the normal to this plane, and we need to find the equation of the plane.
See the equation of the line you're talking about, okay? The gradient, right? Okay,
Yes.
you see the gradient, no? The gradient,
So basically,
the V1 line,
linear approximation.
the linearization,
Linear approximation.
the linearization line will be that V1 only.
Yes, so from this equation we find that linear approximation only, no?
Okay, go ahead.
So what I did here is, you can see here, we got this. I'm unable to do dot product. From what dot product I should do it? If I do it like this, or what?
You have the 6, 2 you have, and then you have this x minus x1 minus, okay, 6, 2 you have, and then you have this x1 minus 3, and then this x2 minus
Yeah, big
1, I suppose. You should be doing the dot product of those two.
Yes. What dot product, sir?
You have the vector,
6, 2.
you have the gradient f, right? The gradient f, that is that 6, and 2. 6, 2 you have, right? fx1,
6,
fx2.
2 dotted with?
6, 2 dotted
Yes.
with the x1 minus 3 and then the x2 minus 1.
So that is not from we are not.
Can you stop sharing? I'll just show you the formula. That's it. Can you stop sharing?
Yeah. So from that dot product, I'm not getting the answer, and I don't think that is right.
Okay, give me a moment.
There's this formula itself is there. It's very straightforward.
Yeah, that's a straightforward one.
Yeah, I know that formula is very straightforward, and I am getting the answer from that formula, but I don't want that formula to work.
Then I don't understand your doubt there. See, we have here f of x star and then the f dash of x star multiplied by this x minus x star, right? So instead of the f dash of x star, you're having the gradient f, and instead of the x minus x star, you're having that that vector transpose. So that is that x1 minus 3 and then the x2 minus 1. That's it, right? It's the same one. Hello, are you able to follow me?
Yeah, okay. I will try it, and I will post it on Discord if I need.
Okay.
Yeah.
Okay. We'll move on to this week 3. Okay. Can you hear me? In this session, we'll discuss week 3. We'll discuss the concepts. We'll discuss first each of the lectures that are there in week 3. Okay, and then we'll move on to the activity questions. And if there is some time, then we'll move on to the practice assignment problems too. Okay.
Okay, sir.
Excuse me, sir.
Okay. All right. So the first thing.
Hello.
Yeah.
Sir,
Yeah.
I have a doubt in second week. Can I ask it?
You have a doubt in where?
Second week, sir.
Second week. Which one? You know, can we discuss that later, please?
I can ask after the lecture. So,
Yeah. We will discuss that later.
Okay, no problem.
Okay. So the first we'll discuss about this four fundamental subspaces: the column space, the null space, the row space, and all. Okay. And then the null space of A transpose. Okay. So the first thing, we have this column space, right? The column space, it is just this linear combination. Okay, the span of the columns. Okay, such that we should be having it as like unique one. So if there is something like repetitions within this column from, so those will be like omitted. For example, you could see here we have, okay, in this particular case we have here 1 2 3 4 1 1 1 2 3 4 5, okay, but then here the columns, the span of columns space of A, that's just 2, okay, because the column 3 is nothing but the column 1 plus column 2, okay. So this column space of A, it is just the span of the linear combination, okay, of this column vectors, okay. Then so whenever we have this vectors right here, you can see here the columns are of R4, okay, this R4, but that does not mean that you can represent each and every R4 vector within the column space. That is, each and every R4 vector need not exist in the column space of A, okay. Here this column space, since here this column 3 is equals to column 1 plus column 2, okay, the independent columns here are only 2 columns. Here we have only 1 and 2 columns, they are independent. So basically this column space of here is it's a 2-dimensional one, okay. So it is subspace of R4, okay, it is a 2-dimensional subspace of R4. So basically each and every R4 vector cannot be represented by the column space of A, okay. Hope that part is clear. No? Yes?
No,
Yes,
sir.
sir.
Could you repeat, please? Could you repeat?
Okay. So if you look at these vectors here, right? Each of the columns here, it is of R4, right? Right? It belongs to this R4, right? Four dimensional vector, right? But
Yeah.
the span of the columns, which is nothing but this column space of A, that does not contain each and every R4 vector, okay. That's because you see here some vectors, it was mentioned here, some vectors in R4 are not in column space of A because Ax equals to B, it has 4 equations and 3 unknowns. It has only 3 unknowns here. So at max it can have like 3 dimensions only, and that too here the column 3 is equals to the column 1 plus column 2, okay. So basically here we have only two independent column vectors here, okay, 2 independent R4 vectors only we have. So basically the column space of A will be equals to the span of column 1 plus column 2, okay. Since the column space of A equals to span of column 1 and column 2, the column space of A is a 2-dimensional subspace of R4. Okay, it is a 2-dimensional subspace of R4, which basically means that all the vectors from R4 will not need not be present in the column space of A. Okay, it's like it's a column space of A is a subset of R4, but R4, all the vectors in R4 will not be belonging to the need not be belonging to this column space of A. Okay, is this fine now? No, still no. Hello.
Yes, sir.
We'll move forward then.
Yes.
So then the null space, it is a subspace of vectors. Okay, it is a subspace of all the vectors that satisfies the condition that X equals to 0. Okay, it should be satisfying the condition that X equals to 0. Then all the span of that vectors, right? Then this will belong to this subspace of this null space. Okay. So suppose if you have these two vectors, two different vectors, ax1 equals 0 and then ax2 equals 0, then both the a of x1 plus x2 will also be equal to 0, right? So basically x1 plus x2 also will belong to the null space of A. Okay. So for example, here if you have like any vector x1 that belongs to the null space of A, then alpha x1, that is a scalar product of the particular vector, that will also belong to the null space of A. Okay. So since we have we suppose for any for anything to be called as a subspace, right, it should be satisfying these two conditions. That is, if one vector if one vector belongs to subspace, and then the second vector belongs to subspace, then the linear combination of those two vectors should also be belonging to subspace. Okay, it actually belongs here. So null space of A is subspace, and similarly the scalar product of any vector, that should also be belonging to the space. So here the null space of alpha x also will be belonging to the null space. So null space of A is also a subspace, similar to the column of A. Okay, the span of columns. Okay, the column subspace. Similarly, the null space also, it is also a subspace. Okay, so if you look for the, okay, so for example, for this particular case, A equals to this 1 2 3 4 1 1 1 2 3 4 5, right? We had here column space of A is a two-dimensional space. So basically it will obviously be having a it will obviously be having a null space. Okay, in this particular example, we said that the column 3 is equals to column 1 plus column 2. So if you construct a vector 1 1 minus 1, okay, column 1 plus column 2 is equals to column 3. So if you have a vector 1 1 minus 1, okay, it will result you Ax equals to 0. Okay, you can check here 1 plus 1 minus 2, that will be 0. 2 plus 1 minus 3, that will be 0. 3 plus 1 minus 4, that will be 0. 4 plus 1 minus 5, that will be 0. Okay, so in total this 1 1 minus 1, okay, that will give you Ax equals to 0. Hence this 1 1 minus 1, okay, that belongs to the null space of A. Okay, and since this is the only vector, okay, the null space of A, it is just a line. Okay, before in the column space, we have here two vectors, column 1 and column 2. That's why it is called two-dimensional subspace. In this particular case, since we have only one vector, that will be a line in R3. Okay. Any questions you have until now?
Sir, this vector 1 1 and minus 1,
Huh?
it's same as saying minus 1 and 1.
Minus 1 and 1. Yeah. So as we told, right, alpha x, right, the null space of A, it is a subspace. So alpha x will be belonging to the subspace. So what you told as minus 1 1 minus 1 1, that is just x multiplied by minus 1.
Yeah.
Okay.
And about 0 0 0 is everywhere.
0 0 0 0 0 0, that is just a trivial solution. Okay, so 0 0 0, that will be there for any matrix. Okay, so that will be like that is a no-brainer solution. Okay, fine. Okay, we look
So what
for
is the linear combination of the columns of A should result in the zero vector, sir? How is this?
see. Okay, if you look at here, right, when I told you that column 1 plus column 2, okay, is equals to column 3, right, which is basically means column 1 plus column 2 minus column 3 is equals to 0. This is nothing but C1 plus C2 minus C3 is equals to 0. That is a linear combination, right?
Right.
That is a linear combination which is equal to 0. So for some constant C1, let's say like okay, let's call this column vectors as C1, C2, C3, C4, and so on, like Cn. Okay, and then the constants with which we are multiplying, let that be A1. Okay, so for Ax to be equal to 0, it should be like A1 C1, A2 C2 plus and so on, An Cn, that should be equal to 0. Okay, basically that linear combination of columns, it should be equal to 0. Okay, am I making sense on this?
So one example, if you could give me.
In this particular, here itself, we could see an example, right? Here you have column 1, column 2, column 3, right?
Yes, sir.
Do this 1 1 minus 1. Here basically what you're doing is you're doing C1 plus C2 minus C3, which is equal to 0. So here the linear combination of these three column vectors, it's equal to 0. C1 plus C2 minus C3 equals 0.
Yes.
Okay. So that is why that's why we are saying that the linear combination of columns of A should result in the zero vector. Should be equal to this zero vector. Okay, in this particular case, the C1 plus C2 minus C3, that will result in the zero vector.
Okay.
Okay. All right. So later, and then this one is important. So if A is invertible, okay, if A is invertible, then that basically means that it will not be having any non-trivial null space, that is only except for the zero vector. Except for the zero vector, there is no other vectors that will be there in the null space of A. Okay, and then this column space of A, that is a whole space. Okay, that is a whole space. So basically, before we said that the column space of A or some vectors in R4 are not in C of A, right? So, but if A is invertible, all the vectors in R4 that can be represented by the column space of A. If A is invertible, okay, keep that in mind. All right. Am I making sense here? Hello.
Sir,
Again?
A is invertible. Please repeat that one.
Yeah, if A is invertible, okay, if A is invertible, then column space of A, it will be the whole space. It will be the whole space. So consider 3 cross 3 matrix. Consider 3 cross 3 matrix. So if the column space of A is a whole space, then what that basically means? The column space of A, it contains all the three vectors. It contains all the three column vectors. Okay. So basically, any of the R3 vector can be represented by this column space of A. Okay, and then the null space of A, it will not be having any solution except for the zero vector, 0 0 0 vector, right? There won't be any other solutions for null space of A. Okay.
Yes, sir.
So can we say, like, if A is invertible, then all the columns are independent, and because they're independent, so the only vector which will result in a linear combination being 0 is the zero vector.
Yeah.
Okay, sir.
Sir, here independent is that rank should be equal to the number of columns, right?
Yes. Yeah.
Okay.
Okay. So if here if null space of A has xn not equal 0, okay, then what they are basically saying here is, then here A is non-invertible. Okay, the null space of A has some solution other than a zero vector. Then Ax equals to B. The Ax equals to B solutions. Okay, it can have solutions of the form xp plus xn, where xn is this null space of A vector. Okay, xn belongs to this null space of A, and then xp is the solution for the xp equals to B. Since axn equals 0 and then xp equals to B, A of xp plus xn also will be equals to B, right? Okay, so that's what they're trying to say. Ax equals to B will be having solution of the form xp plus
Sir,
xn.
can you please explain this statement with some examples, sir, to have a better understanding?
Okay.
This XA inverse B and
So here, just for
Can we
example,
write that beside that one? If you're writing, then it is easy.
yeah, we can able to relate it, sir.
okay. So if you want me to write, so let me just connect this whiteboard then. Okay, give me like 2 minutes. Okay,
Sure.
I'll connect the whiteboard and then we'll start. Okay.
Okay, sir.
Thanks. Okay, can you hear me now?
Yes, sir.
Okay. So here we have this example of this one, right? 1, 1, 2, 3, 4, 1, 1, 1, 1, and then here 2, 3, 4, 5, right? Okay, so this is A. Okay. Here the Ax equals to 0 vector is x vector here is 1, 1, and so here we have 1, 1, and then -1. Okay. So if you consider like Ax equals to B for
Sir, this 1, 1, -1 we will get after doing Gauss elimination like that only, no, sir?
yeah, like that also you will get it.
Okay. Without, by seeing itself, how do you find this, sir? Without doing that Gauss elimination?
This without seeing itself, you will not be able to find it. But in this particular problem, it's easy because the column 1 plus column 2 is equals to column 3.
Yes, sir.
So here, see here, that's why you could see here 1 plus 1. So if you do this Ax equals to B, here 1 plus 1 minus 2, that will equal 0. 2 plus 1 minus 3, that will equal 0. 3 plus 1 minus 4, that will equal 0. So that's why this particular one, it will be holding true. Okay, but for other ones, it not hold true. Okay.
No, sir, I can able to understand. I can understand that 1 plus 1 minus 2 is equal to 0. 2 plus 1 minus 3 is 0 and all. How do you get 1, 1 minus 1? That's not clear.
Okay, how can you say that 1, 1, 2, 2, 1, 3, 3, 1, 4, 4, 1, 5
Yeah.
multiplied by 1, 1 minus 1, right? So this will give you what? 1, 1, 2, that will give you 1 plus 1 minus 2, that will give you 0, right?
0, yes.
2 plus 1 minus 3, that will give you 0.
0.
3 plus 1, 4 minus 4, that will give you 0. Correct? 4
Okay.
plus 1 minus 5, that will give you 0. Right?
Yeah.
Ax equals to 0 form. So this x vector, this belongs to this null space of A, right?
Okay, sir.
Okay. Now
Okay,
let's say that you want to do this Ax equals to B form, okay, where B is equals to, let's say, like 2, 2, 2, 2, okay?
Okay.
This one, okay?
Okay,
So
sir.
for you to get this B equals to 2, 2, 2, no, one solution will be this xp is equals to 0 to 0, okay?
Okay.
This also, let me just show you this. 1, 2, 3, 4, okay, 1, 1, 1, 1, and then 2, 3, 4, 5, okay, multiplied by 0 to 0, it will give you what? 1 plus 0 plus 2 plus 0, 2, and then similarly 0 plus 2 plus 0, 2. Okay, this is what you get. Okay, so this is one solution. Okay, 0 to 0 is one solution. Okay, And then
Okay,
if you have your another vector like this let's call like xp. Okay.
Yeah. Mm.
And this one we call it as xn. Okay.
Okay,
Naturally,
sir.
if you consider the vector xp plus xn,
Mm.
okay, which is nothing but a into this xp plus xn will be what? It's going to be 1
1 1 minus 1 0 2 0
0 2 0, which is going to give you 1
1 3
3.
minus 1.
Okay, yeah, 1 3 minus 1. Okay, even if you do this a multiplied by this 1 3 minus 1, that's going to give you
0, sir?
no, it's going to give you 2 2 2,
2 2 2. Okay.
because ax here is nothing but axp plus axn, right?
AXN. Yes.
Axp is equals to 2 2 2, this one plus 0, which is going to give you this 2 2 2 2,
But
right?
our AXN, okay, AXN is 0 0. XN is only 1 1
AXN
minus.
is 0.
Okay.
Yeah,
Okay.
axn is 0.
Yes,
That's
yes,
why
got it.
that's why we are saying that where are we? Okay, that's why we are saying that if xn has solution that is not equal to 0, I mean that is not a 0 vector, okay, then
Okay.
ax equals to b, which will be having solutions of the form xp plus xn. Okay,
Okay.
all
Okay,
the null space vector can be added to this vector xp, and it not changes the solution. Okay, it will give you a
Oh,
different kind of vector as a solution. Okay,
So how we got that XP vector?
this xp vector you could see here, literally here this is like 2 2 2 2, right, which is nothing but this column multiplied by 2. This column is multiplied by 2, so basically I can remove the other two columns coefficients to 0. Okay, this
Okay,
column
we are
coefficient.
adding XP in the way that we get 2 to 2 for X.
Yeah. Okay, I want this to I want to get, this is my b value, okay, and this is my a value. For me to get this b value, this is the only way, because this b vector is nothing but the 2 times the column of second column,
second
right?
column.
That's why I've written it as like 0 to 0. Okay, clear?
So, sir, second column, it's a linear combination of second column. So what you do is the first column and third column, you make it as 0, and second column, you take it as 2.
Yes,
This is the way to do. Okay, sir.
yeah.
Sir, can you please give the access to the Jamboard, sir? We will copy that to notebook.
Okay.
And so what is this xn? xp is, we have calculated xp, then what is xn?
Which one you're talking about? Xn is this
Another vector. Yeah.
the null space solution.
The null space solution. Okay.
Xn is the 1 minus 1, 1 1 minus 1. Xn is the 1 1 minus 1, the null space solution.
So why are we doing this? That we have to find one vector and then add to the null space. Then what will we get there?
No, we will get the same vector. All we are trying to do is we can have a different solution of the form xp plus xn, not just xp. Axp equals to b, how we have, right? Axp equals to b, how, that's one solution, and all the other vectors of the form xp plus xn will also be the solution for this ax equals to b. That's what we are trying to say. That's it.
Okay.
Okay. Clear?
But sir, here you have written that xn should not be equal to 0. Achha, this is not equal to 0. Got it.
Xn is not 0.
Yes, sir.
Xn is 1 minus 1, right?
Yes, sir. Got it.
Okay. So
Sir, 1 minute. That xn is 1 1 minus 1. Could we go to that Jamboard, sir? Here xn we kept 0 0 0 0. No?
xn, no.
Okay, axn. Sorry.
Axn will be 0 0 0 0. Okay.
Right. Thank you.
Yeah. Okay. So this for finding the null space and all, right, you can be using this Gaussian elimination one. Okay, and actually for the ax equals to b also, you can use a Gaussian elimination. Okay. So here you have this. This is a different example. Okay, you have here 1 2 2 2 4 6 8. Okay, by doing the Gauss elimination, okay, you'll be getting it this form. Okay, this is this upper triangular matrix one. Okay, here the first non-zero values, right? This 1 and then this 2 here. Okay, for the first row, it is this 1, and then this for the second row it is this 2. These two are called as pivot values. Okay, and then the number of pivot values that gives you the rank. Okay, that gives you the rank. Here the first column and then third columns, first column and third columns, they are the pivot columns, and then the second and the fourth column, they are called the free variables. What do you mean by free variables is you can take any values, and based on that values you'll get the corresponding solutions for the x1 and x3. Okay, here you could see here x2 was set as 1 and then x4 is set as 0. Okay, and then you got one solution. Later you set x2 as 0 and then x4 as 1. From there you got one solution. Okay, now the null space of A, it will be the solution, I mean the span of these two vectors. Okay, the u vector, by setting x2 as 1 and then x4 as 0, you got one solution, right? And then by setting x2 as 0 and then x4 as 1, you got one solution. The span of these two vectors u and b, that will give you the null space of A. Okay, since we have discussed here, we have like two pivots, right? And then we have two free variables. Okay, the number of free variables, that will give you the null space of like how many vectors this null space of A has. Okay, or you could call it as like dimension of null space of A.
Nullity also, no sir, we will call it as nullity.
Nullity also. Okay, both the things. All right. So,
sir, could you give some focus on this span, sir? Actually, I forget that one. Match.
The span, like let's say like here you have these two vectors, right? U and V. What do you mean by the span of these two vectors is any vectors. Suppose let's say like you have u vector, u comma v vector. Okay, null space of A, okay, is equals to the span of u comma v. Okay, what we mean by this is if u comma v is a span, then u plus v, okay, or let's say like c1 u plus c2 v will also be belonging to the null space of A. Okay, and then alpha times u will also be belonging to the null space of A. Okay, so basically any linear combination of this will also be belonging to the null space of A. That's what we are trying to say there. Okay, that's it.
But not only UV, there will be some more solutions for this. No?
Yeah, that's what we are trying to say. When we mean by this C1U plus C2B, you'll have like infinite number of combinations, right? And alpha also when you have this alpha U, you can have the infinite number of combinations. Okay, it's not just these two vectors. Okay, that's why we are not saying these are not the only two vectors that belongs to null space. The span of these two vectors belongs to the null space. All right. Even before, one student has asked, right, like 1 minus 1. We only will this be the only vector? Like 2 minus 1. Sorry, 2 minus 2 will also belong to the null space, or minus 1 1. This also will belong to the null space, right? Here, since we have only vector alpha times multiplied by this vector, it will belong to null space. Similarly, if you have two vectors, the linear combination of those two vectors, that it belongs to the null space of A. That's what we mean by the span. Okay, clear on
right,
that?
Sir. All those vector of null space, all the null space is the span.
Yeah. Okay, now this is important. Now the rank is the number of pivot columns. Okay, here you could see we have like two pivots. So for the rank for this particular matrix is 2. Okay, and then the nullity is the number of free variables. Here in this particular case, we have the free variables. These two columns we have like free variables. Okay, column 2 and then column 4. So the nullity will be equals to the 2 here. Okay. Then the other important thing is the rank plus nullity, that will be equals to the number of columns. Okay, in this particular case, you could see here it has 4 columns, right? It has 4 columns. The rank is 2, and then the nullity is 2. So 2 plus 2, that will be equals to the 4 number of columns. This is important. The rank plus nullity will be equals to the n. Okay. The row space is nothing but the ulta or the opposite of it. The column space of A transpose. You do the transpose of you do transpose of A, and then you find the column space of it. Then that is the row space. Okay. So the row space of A is nothing but the column space of A transpose. And then the other important fact is the column rank or the dimension of column space of A or the dimension of row space of A. The row space of A is also represented as column space of A transpose. The column rank, the row rank, and then the rank of the matrix all will be the same. Okay? Clear on that?
Yes, sir.
Okay. So the left null space, this left null space is it's also a similar one. Like previously for null space, what did you say? We said Ax equals 0. All the solutions for x, right? All the solutions for x, those belong to this null space of A. But what about this transpose one? If you call off this A transpose y equals 0, okay, then all the solutions of y, then they belongs to this left null space. Okay, left null space or null space of A transpose. Okay. So just like we have here row space where it is ulta of the column space, we have here left null space. It is just like the transpose. Okay, the null space of A transpose. All right. The next important fact is this: the dimension of column space of A transpose and dimension of null space of A transpose, that will be equal to the number of rows. Okay. We have
I
previously
did not understand the left null space, sir. You're going too fast, sir.
dimension. You did not understand what is this dim, is it? Dimension?
Yes, sir.
Okay. Previously we called about this null space of A is a span of u comma v, right?
Yes, sir.
Here this u comma v, those two are independent vectors. Okay. So here the dimension of null space of A, that will be equal to 2. Or the other way to find out the null space or the dimension of null space is when you do the Gauss elimination one, okay, the number of free columns or free variables you have, that will give you the nullity. Okay. In this particular case, you have 2 pivots and then 2 free variables. Okay. Since you have 2 free variables or 2 free columns, the nullity is 2. The dimension of null space is 2. Okay.
Okay.
Okay. So similarly, when you do that, when you do that for transpose, right, there is a dimension of column space of A transpose and dimension of null space of A transpose, that will be equal to the m, which is nothing but the number of rows.
So, sir, can you be going a bit faster? Can you be a little bit slow, sir?
Like just like we have seen the dimension of column space of A, and this part is clear, right? Dimension of column space of A plus dimension of null space of A, that's equals to n. That part is clear,
Yes.
right? So
Yes, sir.
you do the transpose of it, and then we do the same thing. Okay, and then we do the same thing. That is the dimension of column space of A transpose and dimension of null space of A transpose. Since we have done the transpose, now the columns will be equals to m, right? Correct?
Yes, sir. Yes.
So basically what we are saying is dimension of column space of A transpose and dimension of null space of A transpose, that will equals to m. Okay.
Okay, sir.
And the other important fact we have established is that dimension of column space of A transpose, it will be same as dimension of column space of A or the rank of A, right? So R plus dimension of null space of A transpose will be equals to m. That's what we are trying to say. Okay. Clear on that? No?
Yes, sir.
R plus, okay, sir.
Yeah. Okay. So this one is just an example, like just to cross check with whatever we have is a test of this there. So we need not go to that. Okay, all right. So these are
Will
the.
you share this PDF, sir?
This
is a lecture slide one.
There is just a lecture PDF which is already shared with you.
Okay, sir.
Yeah. Okay. The next important concept is orthogonal vectors. Okay, before we get into the orthogonal vectors, we can look at this length of the vector. The length of the vector, it would be like you would already know that it's just this. If a vector has this x1 to xn, okay, x1, x2, x3, and so on like xn, then the length of that particular vector is nothing but the square root of the or the length square is equals to x1 square plus x2 square and so on xn square. Okay, all right. So this would have been like we have seen it even before, right? So for a vector 1, 2, the length will be equals to.
Is it not root 5, sir? The length of vector?
What?
The length of the vector is root 1 square plus 2 square is equal to root 5.
Yeah. It will be equal to the root, or instead of writing root, you can simply write it as length square equals to x1 square plus x2 square and so on x
Okay. Okay, sir.
They just rewritten it in a different way. Okay.
Sure. Okay, sir.
Okay. So this orthogonal vectors, two vectors are said to be orthogonal if the dot product is 0. Okay. Dot product or the inner product both are same. Okay. So this for the proof is given by this Pythagoras form. Okay. We know that the length of hypotenuse, okay, or the length of this x plus y, okay, that should be equals to mod x plus mod y whole square. They've just they just check that, okay, and then prove that x transpose y will be equals to 0. Okay. So they just like just an expert to say that if two vectors x and y they are like orthogonal to each other, then x transpose y will be equal to 0. Okay. So what do we mean by this? Just the whatever we'll going to see next, like over the next 10 minutes or so. Those will just
Sir,
be
is the reverse will be the same, sir? Like if x
y
is
transpose
orthogonal to y?
y, yeah, that will also be equal to 0.
Same. Okay, sir.
So this you call one vector as x and then the other vector as y, right? You could do it in the opposite way also, right? So
Sir,
that is just a nomenclature. So
I have a doubt actually. X plus y whole square, that modulus whole square, they wrote as x plus y whole transpose into x plus y.
yeah,
We can
yeah.
write like x plus y into x plus y whole transpose, right?
You can,
Transpose, is it required to give it in the first term only, or it
yeah,
can?
it's required to give it in the first term because see, x plus y is a vector, right? Correct.
Yeah,
X plus
yeah,
y is a column vector, correct?
right.
Let's say like it is of n cross 1. Okay. If you have written it as x plus y multiplied by x plus y transpose, then what it will be? It will be n cross 1 multiplied by 1 cross n. It will give you n cross n matrix. It won't give you a scalar value. Okay. But if you have done it as x plus y transpose multiplied by x plus y, now what do you get? You get 1 cross n multiplied by n cross 1 matrix, or this will give you 1 cross 1 scalar. Okay.
Yeah.
So that's why you should be writing it as x plus y transpose multiplied by x plus y. Okay. First is the transpose.
sir,
Yes.
I have a problem that why not in this on the slides.
Okay.
Like why he removed 2.
This 2x transpose y equals 0, then that means x transpose y will equal 0, right? That's what you're asking. Why we remove 2?
Yeah.
If 2x transpose y equals 0, then that basically means x transpose y is 0 now. So there's no point in having to write that constant. It's like saying 2 into 0 is 0, then 0. Then this constant doesn't make sense, right? If 2a is 0, then that means a is 0, right?
Okay.
That's what they are saying here. Okay.
Okay.
Okay. Now this mutually orthogonal vectors, what that basically means is each here, if C1 V1, the linear combination of these two these k vectors, okay, they will be 0. Okay, they will be 0 if and only if all the constants C1, C2, and so on Ck they are 0. Okay, that's because but t downs yeah. So that's because the dot product of mutually orthogonal non-trivial set of vectors is linearly okay. So for the linear combination of these vectors to be zero, okay, each and every constant c1 to be zero. Only then the linear combination will be equal to zero. So those set of vectors, they are called the linearly independent set of vectors. Okay. Previously we have seen u, like whatever we are writing it as span of u comma v, right? Those u and v, they're linearly independent set of vectors. Okay. For example, you could see here. Okay.
But they belong to same null space, no, sir? That u and v.
No, see, individually they are like independent, but they belong to they combinedly they make a null space here. Here 1 2 3 4 and 1 1 1 1, right? So for if you do the linear combination of first vector and second vector, the only way you get a zero vector is if you take c1 as 0 as well as c2 as 0. Okay. So this basically means 1 2 3 4 is linearly independent to the 1 1 1 1 vector. Okay. Same thing here. All right. Okay. So here we could see here the 0 1 0 1 0 0 0 0 1. These are like linearly independent vectors. Similarly, they have given this other examples. Okay. So the orthonormal vectors, two vectors are said to be orthonormal if the dot product of those two vectors are 0, and then each of those two vectors have unit length. Okay, the length of each of the vectors, they should be 1. Then those two vectors are called as orthonormal. They're called like orthonormal vectors. Okay, the examples were given here: 0 1 1 0, and then cos theta sin theta minus sin theta cos theta 1. Okay. The orthogonal subspaces, this is different. Okay, here if you take here x transpose y equals 0, where the x vector belongs to u and then the y vector belongs to v. So basically you take any vector from x from u, and then you take any vector from v. If you do the dot product of those two vectors, it's going to be 0. Okay. For example, here they have taken it as 1 0 0 0 and then 0 1 0 0. Okay, and then this is the u subspace, and then the v subspace is this 0 0 2 1. Okay, you take either this vector. Okay, it's the dot product with respect to this, that's going to be 0, or you take the second vector, the dot product with v vector, that's going to be 0. Okay, so basically this means the u subspace is orthogonal to v subspace. Okay, any vector in u, that's going to be orthogonal to the any vector in v. Okay, all right. So until now it's easy clear.
Yes, sir.
Yes, sir.
Okay, now this could be a little tricky one. Okay, orthogonality with respect to 4 fundamental subspaces. Okay, we have here row 1, row 2, and so on, like row m, right? Okay, so multiplied by a vector.
Actually, in previous term, that u and v are perpendicular to each other, that they are orthogonal. When the w comes, that
Oh no, they're just saying this w, right? The span of this vector 0 0 minus 2 and 1. This is perpendicular to the subspace. Okay.
okay.
Just like this, v is perpendicular to v subspace is perpendicular to u. They're saying w subspace is perpendicular to u. Okay. That's true actually. Okay. Clear?
Oh, right.
Okay. Okay. Now you consider, okay, they're saying here that the row space of A is orthogonal to null space of A. Okay. How is that true? Because you see here row 1, right? Row 1 is perpendicular to x. Okay, because This rho 1 multiplied by x.
Previously, we saw that row space of A is equal to null space of A transpose, no, sir?
No. We didn't see that. We just said that row space of A, right?
Yeah.
Okay. Row space of A, right? It
Yes,
is
sir.
equal, it is nothing but the column space of A transpose. We
Column
just
space of
said
A transpose. Okay, sir.
dimension of row space of
Null
A
space.
is equal to dimension of column space of A. We said that's it.
Okay, sir. Okay, sir.
Which is equal to the rank of A. Okay.
Yeah, correct. Thank you, sir.
Okay. So
I
now
understand.
like this row 1, okay, row 2, row 3, and so on, row like m cross n, right? So m through, okay. And then we have here vector x1, x2, x3, x4, and so on, xn, okay. So what's going to be the first term here? Can someone tell me? It's going to be the this vector, the center vector, let me call it x, okay. This is nothing but row 1 transpose x, right?
Yes, sir.
This row 1 transpose x, this will be the first value here, okay. I'll
Yes,
write
sir.
as row 1 transpose x, okay. The second value will be row 2 transpose x, right? Row 2 transpose x, row 3 transpose x, okay, and so on. Transpose x, okay. So now so consider this vector to be this vector to be the belonging to the null space, okay. So this ax will be equal to 0, correct? Ax will be equal to 0. So basically r1 transpose x is 0, r2 transpose x is 0, r3 transpose x is 0, rm transpose x is 0, correct?
Yes.
Correct? Am I correct with this?
Yes, sir.
So basically each vector from the null space, it is perpendicular to all the rows here, correct? Am I correct on that?
Yes, sir.
Right. So it is perpendicular to all the rows. So row 1 is perpendicular to x, row 2 is perpendicular to x, and so on, row m is perpendicular to x, okay. So this will be holding true for all the null space vectors. So the row space of A, it is perpendicular to the x, right? The row space of A, it is perpendicular to the null space of A, okay. Clear?
So
Yeah.
when we are multiplying, we need not take the transpose of row, right? We just multiply the row with x on the whiteboard.
While if you're writing it this form, that's actually a transpose, right? See, the row vector will be something like this. Okay, so it is 1, 2, 3, 4. Okay, let's say 1, 2, 3, 4. That's a first row, right? So how do you write it in a vector form? The vector form is 1, 2, 3, 4, right?
Okay.
When you're writing it in this form, that's already a transpose, right? Okay, so this is the transpose. 1, 2, 3, 4 is a transpose.
But here we are saying that row 1 is vector.
Yeah,
that's why we are taking the transpose. Okay, got it.
Row 1 is a vector. Row 1 is a vector. That's why if you consider it this way, 1, 2, 3, 4, then it will be a transpose. If you consider it this way, then it won't be a transpose. Okay.
Okay.
It's just a representation form. Okay, nothing more than that.
But then here the actual conclusion is that the vector in like the row 1 is perpendicular to x.
Yes. So this row 1 multiplied by x, that will give you 0. Row 2 multiplied by x, that will give you 0. Row 3 multiplied by x, it will give you 0. Okay, that's the final conclusion. Okay.
Okay. So then the row is perpendicular to x.
Yeah. Each row is perpendicular to x. So the linear combination of the rows also will be perpendicular to x. Okay.
Got it. Yes.
So basically, the row space of A will be perpendicular to x. Okay. And since this is one vector which belongs to the null space of A, the entire span of the null space now, that will also be perpendicular to the row space of A. Okay. The opposite of this is this. The column space of A will be perpendicular to the null space of A transpose. Okay. That would also be clear, I guess. You can just cross check this. Okay. This is an example for that. Okay. The dimensionality check was checked here, whatever we discussed before. The dimension of column space of A plus null space of A, that should be equal to the number of columns. In this particular case, this was the number of columns is 2, so that was checked. And then dimension of column space of A transpose plus dimension of null space of A transpose, that should be equal to the number of rows. Actually, this is rows. So 1, 2, 3. Okay, 3 here. So that was also checked there. Okay. Clear until now?
Yes, sir.
Okay. All right. Now we'll take some short break of like 3 minutes and then we'll continue. Okay. Is that okay? We'll take short break of 3 minutes and then we'll continue. Okay.
Yeah,
Okay, sir.
yeah.
Okay, sir.
Okay, sir.
Thanks. Hello. So yeah, let's continue. Okay. Are you able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So whenever we're talking about this ax equals to b, right? Ax equals to b solutions and all. Sometimes what happens is b will not be exactly lying in the lying in the column space of matrix A, right? Correct. So as I have told in the first so here itself. So in this particular case, the column space of A, it is just a span of the first two vectors. Okay, the first two vectors. So basically, since it is a two-dimensional subspace in R4, not all the vectors in R4 will belong to the subspace, right? So basically, there is going to be some vectors which do not belong to the subspace. So for those vectors, since you cannot find the exact solutions, what you want to do is you want to project those vectors onto the matrix, unlike get the solutions that will minimize the error. Okay. So what do we mean by this minimizing error? Okay, we'll discuss this in a bit. Okay. So in this particular case, suppose we were given this x1 b1 1, okay, and then we have here 2x equals to b1, 3x equals to b2, 4x equals to b3, or this solutions one. Sometimes we will not be getting this exact solutions one. So like I have discussed before, for ax equals to b here, we will not be getting the exact solution because b does not belong to the column space of A. So for those one, we need to be getting this approximate solution that minimizes the error. Okay, so how exactly do we project do we project a vector onto a matrix or onto a different vector? We'll be discussing that. Okay, so if you remember previously, right, like generally when we used to do this okay, we have when you have your one vector, okay, A, and this another vector B, okay, A, B, okay. When you project this, what you do is you drop a vertical perpendicular component to it, okay. This is called the projection of vector A onto B, okay. Or in this particular case, it's like projection of B onto A, okay. So just to make it consistent with respect to the slides, I'm changing to B and A, okay. It is a projection of B, okay, onto the vector and onto the vector A. So since P is not exactly parallel to A, okay, there is going to be some error. Okay, this is the error. Okay, this let me call it as this projected vector. So P plus P vector plus this error vector will be equal to the B vector. Okay, if B vector is like exactly parallel to A, then this error will be equal to 0. All right. So how do you know this projected vector? Okay, this they have written it as x cap A because the projected vector is parallel to this actual vector A. Okay, so that's why they have written it as like x cap A. Okay, the as I have discussed, the projected vector plus the error vector is equals to P. This P plus E, this is equals to B. So the error will be equals to the B minus P or B minus x cap A. Okay. Since we know that this is the vertically projected the orthogonally projected one, that is angle is like 90 degree. E is perpendicular to this to the A. Okay. So if we do the dot product of it, that is B minus x cap A. Okay, the dot product should be equal to 0. So A transpose multiplied by B minus x cap A is 0, which will give you x cap or this projected component, right? That's going to be equal to the A transpose B by A transpose A. Okay. So the projected vector will be in since this x cap should be multiplied by a, that's going to give you a transpose b by a transpose a multiplied by a. Okay. If you okay, so this is the projected vector. Okay, in short. Okay, so there's other simpler way to find out about this. Okay, we'll discuss that. So first thing is this error vector.
So what is the x cap? I didn't understand that x cap is. What is the x cap?
What is this x cap? That is just a constant with which we multiply with a, that gives the projected vector, like
p.
Yeah. So here we have this. This is a projected vector, right?
Yes, sir.
This projected vector is parallel to a, right?
Yes.
So that's why they have written it as like some x cap or some constant multiplied by a. Okay.
Okay.
Just to say that these two are like parallel.
Yes, sir. Yes.
Okay. So this Scottish was.
Can we take E as the magnitude of that particular vertical portion? So that.
Yeah. So that E will be the vector actually. That's not the magnitude. E will be the vector there. Okay. The magnitude of the E vector, that will give you the magnitude of that vertical component. Okay.
Sir, excuse me, sir.
Yeah.
Is this x a scalar or it's also a vector?
X is a scalar there. X is a scalar.
Scalar, yes.
A is a vector. So X is a scalar. Okay. So the length of this vector error, right? The error, the length of that's going to give you this b minus p, or this actual vector minus the projected vector. Okay. Whole square. That's going to give you the length square. Okay. Obviously that should be greater than or equal to 0. Okay. So which is this projected vector? If you rewrite it as like this a transpose b, a transpose c divided by a transpose b multiplied by a. Okay. If you rewrite that, you'll be getting this. Okay. The ultimate inequality is this a transpose b. Okay. The a transpose b will be always be less than or equals to mod a mod b. This we already know, because the dot product of two vectors, they cannot be exceeding the each of the lengths multiplication one. Okay. So A transpose B, it cannot be greater than the mod A mod B. Or in other words.
So come again. What is of two vectors? Which
one?
No, you are saying the two vectors. What quality of two vectors?
The dot product of two vectors, right? The dot product of
dot product. Okay.
Yeah. The dot product of two vectors, A and B. Okay. The magnitude of the dot product, they should always be less than or equal to the individual lengths value, right? Yes. If you have followed the previous week's realization, right? That is the last realization that happened. I told that the dot product of two vectors A transpose B, right? That's going to be equals to AB cos theta, if you remember.
Yes,
okay. Where this theta is the angle between the two vectors. Okay. So this cos theta value, it will always be mod of cos theta, right? So it's always going to be less than or equals to 1. So basically this means A transpose B mod, it will always be less than or equals to the mod A mod B. Okay.
So basically A dot B is basically A transpose B, right?
Yeah.
Yes.
A dot B is nothing but the A transpose B. Okay. So this projected projection projected vector, right, which you got as like A transpose B by A transpose A multiplied by A. If you rewrite it, okay, if you rewrite this, what you get is you get A transpose by A transpose A multiplied by B. This A transpose by A transpose A, that is called as a projection matrix. Okay. This P is called the projection matrix of A. Okay. So if you want to get the projection of like any vector onto A, all you need to do is you need to multiply the projection matrix by that particular vector B. Okay. Is this clear? So it's like it's like I have this vector A. Okay. I have this vector A, and then for this particular vector I find the projection matrix P, which is nothing but this A transpose divided by A transpose A. Okay. So if I know this, I can find the projection of any vector onto A. Okay, suppose let's say like this vector B, the vector C. Okay, I can find the projection of C onto A by doing this A transpose by A transpose C multiplied by C. Okay, or I can do the projection of B onto A by doing this same thing, this matrix multiplied by B. Okay, so through this way, by using the projection matrix, you can project like any vector onto this matrix onto this vector A. Okay, is that clear?
Yes, sir.
Okay, so for example, for this vector 1 1 1, okay, we found the projection matrix. Okay, we found the projection matrix, and then by using the projection matrix, you can like project any vector onto this A. Okay, so if we do the PB, that's going to be the projection of B onto A. Okay, so this P square equals to B. What does that what does that mean is that, okay, so this PB, okay, this P square equals to P we have, right? What that basically simplifies is that BA we have. Okay,
Sir, sorry to disturb you. Sir, I understand one thing, that in the direction of A, it's okay that alpha X hat A. But sir, why B minus? I don't understand that. Why B minus?
Why B minus?
Yes. So if you scroll up, yeah.
This
B
one?
minus, yeah. B minus X dot A. I don't
B minus P. Why this one?
Yes, sir.
Okay. This is A, right? This is the projection, right? This is the projection vector P, right? And then this is the error now. This is the B vector. Okay. So what is this B vector? This B vector is nothing but E vector plus P vector, right? Or in other words, E vector is equals to B minus P now. Okay. That is the error, or the vertical component one. Okay.
Okay.
Okay. So I was talking. Okay, we were discussing about why this P square equals to P, right? So when we do this PA, okay, or when we do this PB, okay, when we do this PB, okay, PB will be equal to this part, right? Okay, but when I mean by PB, that is projection matrix multiplied by B. Okay, PB will be equal to this. Okay, when you again project this, when you again project this PB onto this A, it's again going to be this. Okay, because PB will already be lying on this vector A. Okay, so if we again project it, it's going to be the same. So that's the reason we have this P square equals to P. Okay, PB is already on the line through A, so another route of projection will not be changing it. So P square equals to P. So P square P will also be equals to the PB. Okay, if a vector is already projected, there is even if you project it again on the like 2 times 3 times, it's not going to change the value. Okay. All right. So this column space, the column space of this projection matrix is nothing but this particular vector. Okay, the line passing through the projection matrix column space is nothing but the vector for which we are doing this projection matrix itself 1 1 1, and then the null space is perpendicular to this this 1 1 1. Okay, the null space will be this plane orthogonal to this.
Yeah. One more thing, sir. That P square is that the vector we are projecting again the same vector we are projecting the same vector.
P square is that orthogonal. Sorry, not the orthogonal. The projection matrix you have, right? The projection matrix square.
Okay.
The projection matrix square, it's again going to be the projection matrix itself. Okay.
it is visually, if we want to say that what we taken A is the vector, and we are finding projection of that particular A.
B onto A.
B onto A, sir. But here P square is that we are finding 2 times projecting the same vector again and again, no?
Yeah.
Right.
That's correct.
So P to the power of any number 5, 6, 7, anything, it will be P only.
Yes. That's going to be P only. Correct.
Thank you, sir. Go ahead.
So this is just like another example for this. Even for the A2221, the projection matrix is going to be the same, because this projection matrix, right? The projection matrix, it depends upon the direction. Okay, it does not depend upon the magnitude. So the projection matrix for 1, 1, 1, 2, 2, 2, it's going to be the same. We can actually check that, because the reason why that holds true is, you are dividing that with A transpose A. A transpose A, that takes care of that magnitude part. Okay. Now we'll move on to the next one. So now,
Sir, excuse me, sir.
Yeah.
Sir, if I want to brief the entire projection, so if I am wrong, please correct me. We want to fit a line. If that line is not in the space, vector space, then we are projecting that the other vector which is not in the line or space into that space, and then we are fitting the line.
Yeah. We're trying to project it, like if the B's already not there on the line, we're trying to project it. Correct.
Okay, sir.
So here, for this particular system of equations, right, that is 2x equals to b1, 3x equals to b2, 4x equals to b3. This will only be possible if this b1, b2, b3, they belong to this line passing through 2, 3, 4, or if b1, if this vector b, right, it is equals to alpha times multiplied by 2, 3, 4, then we'll have solution. Okay. Otherwise, we'll not be having a solution. For example, let's say like you want to solve this, 2x equals to 4 you want to solve, 3x equals to 5 you want to solve, and then this 4x equals to 9 you want to solve. Okay, this is basically not solvable, because 2x equals to 4 you'll get x as 2, right? 3x equals to 4 you'll get x as 5 by 3, and then this 4x equals to 9 you will get x as 9 by 4. Okay, this is basically like not solvable, right? In this particular case, what do we do, right? In this particular case, we go for like minimizing the error. Okay, we go for like minimizing the error. What will be the error? This error is just if the error you want it to be 0, then 2x should be exactly to be b1, 3x to be exactly to be b2, 4x should be exactly equals to b3. You want to minimize it, 2x minus b1, 3x minus b2, 4x minus b3, right? That whole square error one, we want to minimize it. Okay, and then like so if you want to minimize this overall value, how do you do it? You just do the differentiation one, and then like you equate it to 0, right? So similarly, you do the differentiation for this. Okay, you do the differentiation for this equation. Then what you get is this x cap 1, it's equals to this A transpose B by A transpose A. Okay, like if you rewrite this, okay, this 2 square, okay, you got this, right? If you simplify this, we will be getting this value 2b1 plus 3b2 plus 4b3. Okay, this is nothing but this 2b1, 3b2, 4b3, that is nothing but A transpose multiplied by B. Okay, and then this 2 square plus 3 square plus 4 square, that's nothing but A transpose A, or the length of A whole square, right? Okay, so basically what we are trying to do is, if you want to minimize the error, all we had to do is we just need to project it. Okay. The same thing which we have like discussed before. So if you want to minimize it, all we have to do is we just need to project it. Okay. So until now what we have discussed is we have discussed about projecting a vector onto another vector. What about like projecting a vector onto a column space? That is a entire matrix. Okay. If you want to project a vector onto a column space of A, then how do you go about it? Okay, so here too the projection of the projection of the vector B onto this column space of A. Okay, that will be given as this AX cap. Okay, where A is that matrix. Okay, or the column space matrix one. Okay, then since this is not exact projection, okay, since this B does not belongs to the matrix, the column space matrix, okay, there is going to be some error. Okay, the orthogonal vector E, which is nothing but the B minus P, which you have seen before, or B minus P, we can rewrite that as like AX cap. Okay, so just like we have seen before, E is perpendicular to the, before we have seen that E is perpendicular to A, right? Now since E belongs to the null space, okay, we know that this E will be perpendicular to every vector in the column space of A. Okay, E is perpendicular to every vector in column space of A. Using that, what we do is we do that A transpose E equals 0. Okay, E is perpendicular to every vector in column space of A. Okay, that's why we are doing the transpose and then multiplying it by E. Okay, we know that this is column 1, column 1, column 2, column 3, column 4. Okay. So okay, let me. So we know that the vector E, it is perpendicular to the column space of A. Okay. So what that basically means is this column 1, column 2, column 3, column 4 multiplied by this vector E. Okay, that's going to give you the 0 vector. That's going to give you the 0 vector. Okay, so how do you get this? This is nothing but the A transpose, right? This is nothing but A transpose, right? So A transpose E will be equal to 0. Okay, so this A transpose E will be equal to 0. Okay, if you rewrite that, we know that this B is equals to this B minus AX. Okay, if you rewrite that, then what you'll be getting is you'll get A transpose multiplied by B minus AX will be 0, or in other words, this A transpose AX cap will be A transpose B. Okay, so the solution for this, it will give you the projection of the B onto A. Okay, this is the same as
one thing. Could we graphically see how it is perpendicular? That could you go in the front pressure one pressure? Yeah. Here, C of A perpendicular to N of A transpose.
C of A is perpendicular to this E. Column space of A is perpendicular to the E.
Here left null matrix. Left null matrix.
E belongs to the null space of A transpose.
Yeah, sir. That
yeah,
how? Yeah.
How is that?
That is the question. How is that? Yeah.
Okay. So what do we mean by this? What is the null space of A transpose? Can someone tell me the definition for this? If A transpose Y is equal to 0, then Y belongs to the null space of A transpose, right? Correct?
Yeah.
Or left null space, right? Yes. So here what we are telling that A transpose E is equal to 0. We are saying that A transpose E equals 0. So basically E belongs to the null space of A transpose, correct? That's what we are trying to say. Okay.
Okay. That error is perpendicular here.
Yeah. So we are projecting onto the column space whatever we have the error, that error will be perpendicular to column space. So if it is perpendicular to column space, that basically means it belongs to the null space of A transpose, or the null space of or the left null space. Okay, clear on that?
So here, just as clear, sir. So I have a very basic doubt, sir, because from math 2, I forgot that, I think. So the column space, what does the column space means actually? Like the vector space formed by, what does that column space means?
This column space, it means that the span of the columns of this vector.
Okay, span of the columns of the vector.
Yeah.
Or the matrix, whatever it is, right?
Okay. So this is just an alternate solution for this. Okay. So we know that this A1 transpose equals 0, AN transpose equals 0. Okay, the same thing. They have rewritten it and then they added the same solution. Okay. Could see here at the end the solution was the same. The important distinction is that A transpose X cap equals to A transpose B. This will give an X cap that minimizes the error. Okay, that minimizes the error. If B does not belong to the column space of AX, okay, through this we'll find a X value that will minimize the error through the projection. Okay? So this A transpose A is like exactly invertible. Okay, if A transpose A is exactly invertible, that happens only when columns of A are independent. Okay? This should be noted down. If columns are A are like linearly independent, that is, if column space of A they form the whole space, okay, then A transpose A is invertible. Then we can rewrite that as this A transpose A X cap equals A transpose B, right? We can rewrite that as A transpose A inverse. Okay, that's it.
Sir, this linearly independent, how we require to take, whether it is like C1 V1 C2 V2 that which we saw previously, or it is regarding that rank of that particular matrix equal to columns?
Yeah. The rank of A is equal to the number of columns. Is equal to the number of columns, right?
Yeah, that is linear independence, right?
Yeah. Then the columns are like linearly independent.
Right.
Okay.
And then it is invertible also.
Yes. Then A transpose A is invertible. Yes.
So if rank of A is equal to number of columns.
Yes.
Okay.
Okay. Now through this we can directly get this X cap, and from the X cap we can get the projection P as AX cap is A multiplied by this A transpose A inverse A transpose B. Okay. Clear? Okay. So now until now we talk like this, just like different scenarios. If B already belongs to the column space of A, if B already belongs to the column space of A, then B will be equals to AX, right?
So can we do a question, sir? We understand what the theory we have learned.
Okay, we'll do that later. Okay, after discussing that, we'll be getting into that. Okay, after discussing this, we'll have like one more lecture where we entirely discuss about the problem. So we'll get into that. Okay. If B already belongs to the column space of A, okay, then the error will be 0. Okay, so here we are talking about if B already belongs to the column space of A, right? Then this B minus P will be 0, right? Or okay, so this projection itself, it will be equals to B. Okay, this projection itself, it will be equals to B, right? Or in other words, it's A transpose A inverse A transpose A, right? This ender one, this will be equals to I. Okay, they have written this. We have this A transpose B, right? They have written this B equals to AX. Okay, in place of B equals to AX, they have written this they have got it as like I, and then this AX equals to B even. Okay, which will give you the projection as B itself. If B belongs to the column space of A, then we already know that the projection will be equals to B. Correct? Only when B does not belong to the column space, then we had to do the projection. Okay. So if B belongs to the null space of A transpose, when we mean by null space of A transpose, what we mean is if B vector is like entirely perpendicular to the column space. If B vector is entirely perpendicular to column space, then the projection will be 0. Then there is not going to be any projection there. Okay. So here this A transpose B is 0. Okay. So this entire projection will become 0. All right. So if A is square and invertible, okay, if A is square and invertible, what does that mean is, okay, if A is square and invertible, then the column space of A, it belongs to the, it contains the entire dimension, okay, it contains the entire dimension. So previously, okay, wait. Let's consider like one 3 cross 3 matrix, okay, 3 cross 3 matrix whose rank is 3, okay, whose rank is 3, which implies the dimension of column space of A is 3, right? If the dimension of column space of A is 3, then we can write any R3 vector, any R3 vector will belongs to the column space of A. Okay. If any R3 vector belongs to the column space of A, then the projection of any vector, onto the column space, that will become the same vector itself. Okay. So if A is a square matrix and it is invertible, then the projection of any matrix, okay, sorry, then the projection of any vector onto this matrix, that will be equal to the vector itself. Okay. This is the fourth statement. Is that clear?
No, sir. Repeat that.
No, sir.
Okay. Okay. So let's come back here. Here in this particular question, right, A equals to 1 2 3 4 1 1 1 1 2 3 4 5. I have told that column space of A is we have told that column space of A is the span of the first two vectors, right? Span of the first vector and second vector, right? This first column and second column, right? Correct?
Yes, sir. Yeah.
Yes,
Here
sir.
I have told any vector in R4 need not be belonging to the column space of A because the dimension of because C of A, it has only two dimensions, right? It is only two-dimensional plane. Okay. Or in other words, the dimension of column space of A, it is only 2. Okay. But we have, that is the reason we can't represent any R4 vector in this column space of A. But let's say I need to represent R3 vector, okay, in a column space whose dimension is 3. Okay. If it is a span of like 3 vectors, then I can represent any vector, any vector within this column space itself. Okay. Then I can represent any vector within this column space. So that is the reason. If I can represent any vector, any vector within the column space, okay, then that basically means the projection will be equals to B. Okay. Correct. Is this clear? No, still.
Yes, somewhat, sir. Okay.
So
I mean, if all the columns, if we have a span of all the columns, then we can able to project on to the B.
Yeah. So
Okay.
like let's say like you have this 3 cross 3 matrix, 3 cross 3 square matrix. Okay. It is invertible. So basically rank n is equals to rank is equals to the dimension of the column space of A. It is equals to 3. Okay. If the dimension of column space of A is equals to 3, then you can represent any R3 vector in the column space of any R3 vector. It belongs to the column space of A. Okay. So basically,
Yes.
In that particular case, you will be getting a any vector. It will already be like presenting in the column space of B. Okay. So the projection of any vector will be equals to B itself. Okay. There
My
won't be
basic doubt is, sir, all the invertible matrix or square matrix, no, sir?
Yes, yes.
And why do
all,
we specifically mentioning that square and invertible? A is invertible. That includes square, no, sir. Is or any the reason for that? Square and invertible.
Yeah, actually, if it is like invertible, you need not mention it. But if
Okay.
it is a square, then it need not be invertible, right? So.
Okay, sir. Oh, the reverse is not true. Okay.
Yeah, the reverse is not true. All the square matrices are not invertible. So.
Okay, sir.
If A is of rank 1, then this is the previous situation which we have seen. A transpose B by A transpose A. Okay, the X cap one. Okay. The projection matrix, the previous one. Okay. So in general, in general, this is the formula. Okay, for finding this projection. Okay. So the p square equals to p. This holds true. This holds true even for the span of the columns, or even for the single vector. This p square equals to p, that will be holding true. Okay, and then this p it will always be symmetric. Okay, just like we have seen for the single vector, p is going to be symmetric.
This p square is equal to p. That if we see that, we can dissolve that one into identity matrix also, no? P square. That.
P square equals to p. See, the thing is, identity matrix, or just because p square equals to p, that does not mean that p is identity matrix. But for identity matrix, p square equals to p holds true. For identity matrix, I square equals to I. Okay, but p need not be identity matrix here. Okay.
Okay, right.
So here too, the reason why p square equals to p is holds true is when a vector is already projected, okay, even if it is projected again, that will still be the same, right? So that's why p square will be equals to p, or p power n will be equals to p. Okay. All right. Okay. Now we'll be looking at few examples. So in this particular case, we want to be solving this bi equals to theta I xa, and then this theta double dash. Okay, so this theta 1 and then this theta 2, these are the values which we need to be finding. Okay, all right. So for you to be fitting it, or like for you to be getting the getting this exact values, right? So what you do is you rewrite that in a matrix form. Okay, ax equals to b thing. Okay, or a theta equals to b. Okay, you try to find which gives the least error. Okay, same thing, this theta 1x plus theta 2, right? This is actually a linear line, right? So like for example, whatever we have, x1 comma b1, this is a point. x2 comma b2, that's second point. x3 comma b3, that is the third point. x4 comma b4, that is a fourth point. Okay, so here what we're trying to do is we are trying to fit a linear line with this. So by linear line, what we mean, so we want to find a line such that x1 theta 1 plus theta 2 is equals to b1, x2 theta 1 plus theta 2, that's equals to b2, okay, x3 theta 1 plus theta 2 is equals to b3. Okay, so basically you're getting it right. This theta 1 is a slope, mx plus b form, y equals to mx plus b form. Okay, so where this m is the theta 1 and then this b, this constant is theta 2. Okay, so given a points, we want to find a line. Okay, we want to find a line such that it will give the least error. Okay, if all these points form exactly in a line, then the error will be 0. But I don't think they'll always form exactly in a line. Okay, so for this, the way you solve is the same thing. You rewrite this entire thing in a matrix form. This ax equals to b form, where this x1 to xm they belongs to this x coefficients one, and then for this one is this offset, okay, the constant one. So this theta1, theta1 is the slope, and then this theta2, that's this constant one. Okay, this will be equal to the y coordinates. Yeah,
I have a doubt here actually. Here x1 comma b1 is a point there.
Yeah.
Why we want to write that one b1 is equal to theta x1 plus theta? What is that?
This is this y equals to mx plus b form.
Okay.
Linear line form, right? Y equals to mx plus b, the line, right? Straight line.
Okay, we want to linearize that particular point.
Yeah. We want to linearize this particular data itself. We want to find a straight line equation such that the error will be like very least.
Okay.
Okay. So you have rewritten this in the form of this ax equals to b. Okay. Now our goal is to find the theta that minimizes this. Okay. So if this b vector, if it exactly falls in the column space of A, right, then the projection will be b itself, and then you will not be getting any error. But if the b vector does not belong to the column space of A, then there is going to be some error, right? Okay. So a theta equals to b, it may be inconsistent. By maybe inconsistent. What they're trying to say is it may not have an actual solution. Okay, we might need to be projecting it. Okay, so we'll be looking at this error thing, b minus a theta whole square, and then this we want to minimize the b minus a theta whole square, right? So the same thing we'll be doing. Okay, the same thing, a transpose a theta equals to a transpose b, same thing which we have seen before. Okay, we do this a transpose a, the points were given here. Okay, this minus 1 comma 1, and then 2 comma 3. Okay, those are the points there. So using those points we can find the a transpose a, and then the a transpose b was like find out. Okay, by using a transpose a and a transpose b, we can find the theta 1 and then theta 2, both will find out. So in this way we were able to find out the m and the constant y equals to mx plus b. We are able to find out that slope and then the constant that minimizes the error. Okay, that not make the error to be 0 because it is not consistent. Okay, it's not consistent here. The error was not made to be 0, but the error was minimized. Okay, so here in this particular case the projection says this for the first case, for the -1 case. Okay, -1, right? The projection is -1 into 4/7 plus 9/7, which is 5/7. Okay, but the actual value is 1. Okay, the actual value is 1. For 0.2 the projection is 13/7, but then the actual value is again 1. Okay, for 0.3 the projection is 17/7, but the actual value is 3. Okay, so there is an error there. Okay, so the error 2 was found out here. Okay, so this can be.
So capital E and small e, what is the difference? This one here.
This capital A and then the small a one.
Yeah, capital E and small e.
This both should be the same. Both should be the same. Okay. We look at this. E is the vector there. Okay, E is the vector there. This e square is the magnitude there. Okay, this capital E square, right? Capital E, that capital E which you are seeing, right? That's a scalar one. The small e which you are seeing, that's a vector.
Okay.
Okay. This E is kind of like the actual error scalar value, but small e is the difference between the actual y value and then the expected y value. Okay.
Sorry, is it a squared error?
What?
Is that a squared error?
Yeah. The capital E which you are saying, right? That's a error value. That's a scalar value. Okay. But then the small e which you are seeing there, that's a vector. That's a vector whose length whole square will be equal to the error square, capital E square. Okay.
Okay, sir.
Yeah. Okay. So the point through in this way we can be doing the projections. Okay. By projections, what we mean is like we can be trying to minimize the error. Okay. If we do not get the actual solution. Okay. Clear on this? The problem statement, we did not actually solve this, but the solution is like straightforward. Okay. Is this okay?
Yes, sir.
Okay. Look at the problems. Okay. And then like go through the slides again. Okay. We'll have next session on the next Thursday. So if we still have doubts, we can be discussing that. Okay. Now we look at the activity questions. Okay, now this. So column space of a row space of a null space of a denote the column space, row space, and null space. Which the following species, which the following are true about column space of matrix A? Consists a linear combination of columns of A transpose? No. Column space of column vectors of A? Correct. Is a span of column vectors of A? Correct. The third one is the last one is incorrect. If X and Y belongs to the null space of A, then the linear combination of X and Y will belong to null space of A. That's true because null space of A is subspace, so that holds true. So the following is true about the null space of matrix A. It is those B for which Ax equals to B has a solution. That's not true. It is those. Yeah.
Ax equals to 0.
Okay. A vector X belongs to null space of matrix A if Ax equals 0. The same thing. Gaussian elimination changes the null space of matrix. No, it does not change. N cross N matrix is invertible, then which of the following is true? If it is invertible, then the column space of A is Rn. That's true. Ax equals to B has infinite solutions. Ax equals to B has a unique solution. This column space of A is Rn. This is true. This 2 should be true. Ax equals to B has a unique solution. This will also be true. So actually, okay, is that false? Okay, is that false? They're asking. Okay.
It is asking for false, sir.
Okay. Ax equals to B has infinite solution. That is false. Okay. Ax equals to B will have a unique solution. Okay. No matter what the B is, it will have a unique solution. Okay. This is also another way of saying we can represent any vector, any vector, like or any vector will belong to the column space of A. Okay. If A is invertible. Okay. This is another way of saying it has a unique solution, right? So basically, any vector can be represented in the column space of A. Okay. Which of the following is true about M cross N matrix A? Dimension of column space. Yeah. The second one is false. Rank of A and nullity of A is equals to M false.
True. True.
Yep.
False.
Yeah, that's false. The following statements regarding the rank of matrix. Rank of matrix equals to dimension of column space. True. True. Second one is true. The third one is equal to dimension of its null space. False. Rank of matrix is equal to columns of matrix.
False.
Number of columns of matrix, that's false. The 1 and 2 are true. Okay. So let's check. Okay, yeah, we are fine. We are fine there. X dot y denote the inner product between the vectors x and y. The length of the vector is x transpose x. Okay. Xx transpose, it will not give you the length. Okay, it will give you a matrix. Two vectors x and y are orthogonal if x transpose
y equals to 0.
Yeah, x transpose y equals 0 or
Y transpose x equals to 0. Third one.
And x dot y is equal 0 and y dot x equals 0. Okay. Which of the following vectors is orthogonal to any given vector? 0 vector is orthogonal to any given vector because A transpose 0 vector, it will always be 0. Okay. If two vectors x1 and x2 are orthogonal, then they are not linearly independent. Then actually they are linearly independent. So it's two vectors are orthogonal to each other, then they are not linearly independent. Actually, that's true. They're dependent. So two vectors x and y are orthonormal if x dot y is 0 and then mod x mod y is equals to 1. So two subspaces.
Sir, please explain a little bit slow, sir.
Okay. So we have discussed that if vectors are like orthonormal, then the dot product of those two vectors, first of all, the vector should be orthogonal to each other. That is, x dot y should be equals to 0. And then the length of each of those vectors should be equals to 1. So option B is correct. Okay. Option A is incorrect because the mod x and mod y cannot be 0. Okay. So two subspaces S1 and S2 are orthogonal. This is also definition 1. So two subspaces are orthogonal if x transpose y equals 0, given that for all x belongs to S1 and for all y belongs to S2. That's correct. Second one is false because x transpose y equals to 1 will not happen. Okay. Third one is false such that it's not such that it should be for all. Okay. So it is just like they have just given the permutations of this such that means for all. Okay, just to confuse you. Which of the following statements, which of the following is a true? Open denotes orthogonal complement. Column space of A is perpendicular to null space of A. That's not correct. Row space of A is perpendicular to null space of A. That's correct. Column space of A is perpendicular to null space of A transpose. That too is correct. Okay. Yeah. We'll move on to the next one. System of equations Ax equals to B is inconsistent. If it will be inconsistent if B does not belongs to the column space of A, right? So the column space of projection matrix of vector projection matrix of a vector B is a line parallel to a line passing through B. Okay. The line parallel to the line through B.
For the second one, the column space of projection matrix of vector V is.
Okay, so this you see here this vector A111, right? So for this particular one, the projection matrix P we have. Okay, so it was clearly mentioned that the column space of the projection matrix, right? That's going to be the line through 111. Okay, so you can see here the projection matrix here is 1 by 3, 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 and then this same thing. Okay, this is nothing but a single vector, right? A line through this 1, 1, 1, right? All right. So basically, the column space of projection of matrix of a vector V is a line passing through the V. Yes. Okay. A line through V. Yeah. Consider the following statements regarding the projection matrix P. P square equals to P. That's true. P is symmetric. That's true. So the 1 and 2 are correct. A null space of projection matrix of B is here too. If the column space is a line passing through B, then the null space will be a line perpendicular to the line through
Perpendicular
B. Okay?
to the line. Yes.
Yeah. So these two was discussed here. Plane orthogonal to the 1, 1, 1, or in other words, a line perpendicular to the line through B. Okay. Okay. A plane. Okay. Sorry, it's not a line. It's a plane. It's a plane orthogonal to B. It's not just a line, right? So it will be a plane. So the projection of matrix P of a vector A is given by the projection matrix P of vector A is given by the same one, A transpose by A transpose A, or A transpose A is nothing but length of A whole square. So this will be derived like this. Yeah. So that's what. Let's check. Okay, very good. This incrossant matrix is invertible. If incrossant matrix is invertible, then the column space of A, it is Rn, correct? The rank of A is Rn, correct? The rank of A is equals to n. Okay, so all of these are correct. Consider Ax equals to be the projection of matrix A is an identity matrix if the projection matrix of A is an identity matrix if B belongs to column space of A. Okay, so this basically what they're trying to say is the projection of any vector, right? It's PB, right? Okay. If this P is an identity matrix, okay, if it is an identity matrix, okay, then the projection of any vector PB that's going to be equal to B, right? Correct. So when will that be true? When will the projection of a vector will be equals to the B itself? Then that will only be true when B belongs to the column space of A. Okay.
When A transpose A is equal to A into A transpose, then this identity matrix will come.
Come again.
If A into A transpose into A is equal to A into A transpose.
A transpose equals to A into A transpose. Then this identity will come into picture. You're saying?
Yeah. Then only this identity will come.
I don't follow you. Sorry. How are you saying this?
Because projection of A is equal to A transpose A by A into A transpose into that particular vector.
Okay, sorry. A transpose by A transpose A. Yeah.
A into A transpose by A transpose A into that particular vector. Then it is the projection. So it required to be one, then both required to be equal.
Actually, we cannot exactly do this. Like we cannot say that this is a matrix, right? First thing is this is a matrix, right?
Okay.
Okay. So what you're trying to do for this? This is for a single vector A. Okay. So here if it is A transpose by A transpose A, okay, it is A transpose by A transpose A transpose A. Then here too, this A transpose will be a matrix. This is a scalar.
Right.
This is scalar. Okay. You cannot actually be doing it like you do for the normal integers and all. Okay.
Okay.
Yeah. But if you just follow this, you'll be knowing that PB equals to B. If P is an identity, then we know that PB equals to B. Okay. So if for any vector, if the projection is the same vector itself, then the B should belong to the column space of A. Okay. Consider the following statements regarding the projection matrix. P transpose equals to P. That's true because P is symmetric. P square equals to P is true. So the 1 and 3 are correct.
Sir, what about symmetry of that particular matrix, sir? Could you explain that symmetry?
Which one? The symmetry of the projection matrix?
Yeah.
See here, let's say like you're forming a projection matrix from a single vector, okay?
Okay.
A transpose, okay? So it's going to be like something like x, y, z, okay? Multiplied by x, y, z, right? So what do you get? You get x square, okay? X square you get xy, xz, xy again, y square, yz, then this is going to be zx, zx and then zy, and then z square, right?
Yeah.
These two are same.
Yeah.
These two are same.
Right, sir.
These two are same. So basically it is symmetric matrix, right?
Okay.
Okay.
Right.
So anything like AA transpose, right? It will always be symmetric. So until now we are good. A theta B equals to has a solution. If it has a solution, right, then that basically means A theta minus B whole square, that is the error part, it will be 0. So this second option is true. The least square solution to a system of linear equations A theta B equals to B is aims to minimize A theta minus B. We always try to minimize the error, so aims to minimize A theta minus B. Okay. The least square solution to a system of linear equations A theta equals to B projects B onto the row space of A wrong.
Column space of A.
Yeah, that's correct. So we will not be discussing the practice assignment, okay? What we'll do is we'll discuss the practice assignment as well as solve with instructor in the next session, okay? All right. So any other questions here?
No, sir.
Okay, then so yeah, thanks everyone.
So can you share this PPT that you are writing on?
This PPT, it's already shared with you guys. So okay, let me just copy the link and then
Yep, that would be,
chat box, okay?
that would be great.
You can get in the supplementary content.
Yeah, we'll try to add it there too, okay?
Thank you.
All right, so it was shared with you. Okay. All right.
Okay.
Thanks everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.